Hello, Simon. Today we're going to talk about the most important, the most essential equation in quantum mechanics, the Schrodinger's equation. You probably have heard of it before. It is an equation divided by Schrodinger. So what is it for? So a Schrodinger equation is a wave function. A function that describes a wave. And what does that wave describe is the probability distribution of a particle in that region of space. So imagine we have a particle and we only consider it in one dimension of space, this wave. When there is a large amplitude in this wave, in this bump of curve, will be very likely to find our particle there. But if there is a very small on the edge of the wave with a small amplitude, the particle will not be very likely to find there. So wave function Schrodinger equation describe the probability distribution of how likely a particle or multiple particles will be found at a certain region of space, one place. So we use a symbol called psi, and it's a multivariable function, which we use two variables, x and t. T represents time, x is the space. So it's a one particle situation, Schrodinger equation. And we define the probability of the particle in that space to be the square of our Schrodinger equation, because the wave could be negative, but probability cannot be negative, so we simply square it. And the absolute sign is not just absolute sign, it is called the normalization sign, because after we dig deeper to the equation, we know that the function is actually a complex number, have an imaginary number. So we need to find some way to normalize it into a rational number, real number, and then square it. If it's negative from positive. So we know it's a wave function, have to be something about sine and cosine. But we don't know the exact shape, or we don't know exact behavior of the wave. So it's very hard to directly derive it out of cosine and sine. So we need some motivations. Let's recall e to the ix is equal to cosine x plus I times sine x, which is our beautiful, beautiful Euler identity, if you remember. So on this equation, we can talk about sine and cosine simultaneously. And also it's easier to differentiate because we have e to the x. As long as you have e to the x, when you differentiate it, come back to itself. So it's a very simple and trick to use in the future. And also we can review some of the wave behavior, which we'll see later. So let's now express our general motivation, intuition of our wave function. It's equal to e to the I times kx minus omega t. So kx represents the amplitude or the frequency of the wave, and then omega t defines the phase shift of the wave, the travel over time. So we can see here this wave and it travel through a little time. Oh, we shouldn't use lambda. That's a mistake. We can use that. That's the wavelength. This is our omega, the speed of the wave. So how are we going to find k and omega in order to define our Schrodinger equation? We can see that's what we're going to do next. So first we know that the wave have symmetries. If you have identical wave, at every peak the value should be the same, and every cross the value should also be the same. So before that, let's recall a physics concept. The Debroglie wavelength is equal to the Planck constant divided by the momentum of the object. This is called the Debroglie equation. It says that all the matter in the universe are both wave and particle, wave-particle duality. And if it's a wave, there will have to be a specific wavelength associated with that object, which is very, very small because Planck constant divided by the momentum, is very small. So that's why we consider it quantum scale. So maybe this wavelength has something to do with the wavelength of our actual wave function, like between two peaks of our Schrödinger's wave function. There have to be the same value, and the distance between it need to be lambda, let's say. So how are we going to find lambda? Because of the spatial symmetry of the wave function, we know if we phase shift our function spatially to the right lambda distance, the value should remain the same. So we can find an equality down below. E to the I times k times the lambda plus x minus omega t should be equal to our original psi function. So let's do a little bit of simplification. On the left hand side, what we got is e to the I times k lambda plus I times k of x minus I times omega t is equal to e times I times kx minus omega t. So let's factor out the e to the I k lambda. We got 2 psi on the left and right equation, the original equation. So we know that e to the ik lambda have to be equal to 1 in order for the equation to be correct, to be compared to the original equation. So we know that e to the ik lambda have to be equal to 1. So how are we going to do that? Don't forget, we have our old friend Euler identity. Here's what the mathematical beauty come into the equation. The Euler's identity that e to the I pi is equal to negative 1. If we square it, it becomes 1. So we can say, equate them together, we have e to the 2 pi I equal to e to the I k lambda, which is equal to 1. Then we have 2 pi is equal to k lambda. Then we know lambda will be equal to 2 pi divided by k. As here we saw before, we know lambda is also equal to Planck constant divided by our momentum. This is our Debroglie wavelength. So we know that the Planck constant divided by p, momentum, will be equal to 2 pi divided by k. K is the constant. So now if solve for p, we know p will be equal to h times k divided by 2 pi. And because Planck constant divided by 2 pi pop out a lot in physics, so we define it as a bar of Planck constant, bar h. Bar h is defined as h over 2 pi. So we can rewrite the function as momentum is equal to bar Planck constant times k. So here we got a very important result here. Okay. So what we just did is we use the spatial symmetry property of wave to solve for the spatial constant k. So now we are going to use the time symmetry in order to solve for the time variable, the velocity of the wave, omega. So now we use time symmetry of wave. So we need another intuition here. Last time we used our old friend momentum. This time we're going to use energy. So if we recall our Einstein's function of energy, now equal mc squared by E equals Planck constant times wave times the frequency, which is the photoelectro effect. It's actually what Einstein get his Nobel Prize for, not for general relativity, but for the photoelectro effect. And we, according to the symmetry of wave, that it in the first time and the second time the wave reaches its peak, the two peak value should be the same. And over the translation of change in t, which is equal to the period, and period is equal to the inverse of the frequency, we know the value should be the same. So t, we transfer a little time over one period, which is t plus 1 over mu. Mu is our frequency. Not mu, I think. Now divide by our frequency. Never mind the same old name. Then we will have our omega t. Let's trust our original equation. Omega t will be transferred to omega t plus omega divided by the frequency. Then let's plug into our original equation, original Schrödinger equation. So let's recall. Of our equation equal to e to the I times kx minus omega of t plus a 1 over frequency, which will be our phase shift of time. Then theoretically, that should be returning to our original value, which is e to the I of kx minus omega t. Then we expand it out, we have e to the I kx minus omega t minus 1 over the frequency. Oops, I think I forgot to add item. Okay, now we do. So we have e is equal to the e to the I times kx minus omega t. Right side, don't change, it's still the per side. Then let's keep expanding out the left hand side. We'll have e to the I kx minus omega t times e to the, that should be omega, not 1, that should be omega, forgot. E to the negative I times omega divided by the frequency will be equal to e times I times kx minus omega t. Then we know that this value have to equal to 1 in order for the equation to be hold. So let's use our old friend Euler identity again. The square of Euler identity is equal to 1, and we plug in back to our equation. So we have e to the negative I omega divided by the frequency is equal to e to the I pi equal to 1. Then we will have omega over the frequency equal to 2 times pi. Then, well, because the frequency should be a positive number, there's nothing else, negative time or something like that. So let's choose the square of this number. Choose the absolute number of this frequency. So we will get the frequency will be equal to omega over 2 pi. Okay, so now we solved for the frequency. But we now need to plug it back to our energy equation. Energy E is equal to Planck constant times the frequency. So now we know the frequency. Let's plug into the energy equation. We will have E is equal to h times omega divided by 2 pi. Then we will know omega h divided by 2 pi is bar Planck constant. Then we will have E equal to bar h times omega. Now we have both our energy equation and momentum equation. Seems pretty amazing, right? Just deriving some Euler identity, we can get out some physical sense of energy and momentum from Schrödinger equation. It's amazing. So now we are going to really try to solve our equation now. Now we get all the intuition, all the motivation we need. Now we need to solve for a situation in non-relativistic form of our Schrödinger equation. It's non-relativistic. All the things keeping classical physics. Then we know our classical physics, Newtonian mechanics, momentum is equal to mass times velocity. And the kinetic energy will be 1/2 times m times the square of v, the velocity. So Ke, the kinetic energy, will be equal to mv squared divided by 2m, will be equal to the square of our momentum divided by 2m. And let's recall our momentum is equal to bar Planck constant times k. So let's plug it in. We know the energy will be equal to bar Planck constant times k and all the square divided by 2m. And we know our energy equation is equal to bar Planck constant times omega. So bar times omega will be equal to bar Planck constant times k all of 2 squared divided by 2m. So that's our second very important result. So now, what's our next? Next, we need to solve for k and omega. So we need to find out how to express our constant in terms of the thing we already know. So let's first try to find an expression for k, our spatial k, spatial constant k. So let's recall our original function. Psi of xt is equal to e times I times kx divided by and minus the omega t. Then let's use a little trick to try to differentiate this function. We'll have the derivative of psi over x, the space, because we're solving for spatial constant, we differentiate it according to space x. Then we'll have I times k times the original psi equation. Because it's e, so the rest power don't change, and we have our chain rule, just move the inside thing out. Then let's take the second derivative. It seems not enough. We have the square of I will just be equal to minus 1. Then we have k move out again, so we have minus k squared times the original psi equation. Think we find an expression for k, although it's a differential equation, but we find it. We finally find that k is equal to let's keep it here. Let's keep it in this form. It's already pretty simple, so let's don't make it too complicated. Then now, after we solve an expression for k, we are going to try to solve our expression for omega. Before that, we need to record this very important result, which is the equivalent of energy and momentum. And we need to use these two expressions to build up a new expression. So let's see what is our new expression looks like. Well, we have a new expression equal to the bar Planck constant square, the minus, divided by 2m, times the second derivative of our psi function is equal to bar Planck constant times k all the square divided by 2m times the psi function. So how did we get this result? So we can see seems like we just plug in the right side equation of our energy momentum equivalent equation into the right hand side of our differential equation. Then because we have some additional term on the right, which is a negative sign, and also we have our bar Planck constants and 2m on the right is added out. So we just multiply both sides by this function. So we have moved them to the left of the equation. Then we see this is an equivalent form. And that is what we want here for the Schrödinger equation. Why? We'll see later, because we need to find some equivalent of energy. Then we need to try to find the equation for omega, the time variable. Let's recall our Schrödinger equation again, which is equal to psi of xt is equal to e to the I times kx minus omega t. And let's differentiate it. This time we differentiate it over time because we need to find expression for a time variable. Then we, because e to the some number differentiated just back to itself, we have negative I omega times psi of x over t to t. Do we need a second derivative? No, actually we do not, because we already have our expression for omega. We have an I here, but it's okay. We can multiply both sides by I, and then multiply both sides by bar Planck constant. Why would I do that? Because we want to set an energy equation on the right hand side, so that we can equivalent the two expressions on the right hand side. The expression we just derived before based on the energy momentum equation and our expression for k. So what I mean by that, if you see the right hand side of the constant term of our omega expression with our previous energy expression, the space expression for constant k, we know that, let's paste it here, we have our omega times bar Planck constant is equal to the bar Planck constant times k all the way squared divided by 2m. So these two functions, as I trace out, are the same. They are equivalent because their constant term are both describing energy, and the function is just psi. They are both psi. So we can connect two left-hand side together. We'll have our final expression. I times bar Planck constant times the second derivative, times the first derivative of our psi function is equal to the negative times our square of bar Planck constant divided by 2m times the second derivative, our psi function. And that's our Schrödinger equation for one particle moving in one-dimensional space in non-relativistic form that's not acting on by the force. It's a differential equation though. It's pretty cool.